Is the resistance of soil in Lincolnshire actually different to the soil over here in Yorkshire? And does it really matter? Probably not, but in this video we're going to find out. And we're going to find out by testing this 91 square metre patch of soil. And answer the question, can you put a substation anywhere? Do parallel paths in the ground really skew earth readings by a massive amount? And is it really possible for a TT system to be poor in Netherwallop but excellent in Penistone? So let's find out. Oh, and did you know that this video is available as a free CPD? You can head over to Trainer Central where you can bag yourself a certificate. I've left links in the description. Before we talk about earth rods, electrodes and the test results, we need to talk about the ground itself, because resistivity is the property of the soil, not the metal that we drive into it. So what do we actually mean by soil resistivity? Electric current can flow through soil because moisture in the ground contains dissolved salts, and those salts allow ions to move, which is what carries current. That means the ability of the soil to carry current depends on how much moisture it holds and how easily that moisture can move. And this is where resistivity comes in. Resistivity is a measure of how strongly the soil resists the flow of electric current. Low resistivity means the current spreads easily. High resistivity means the current struggles. And the resistance does not come from one thing, it comes from the structure of the ground itself. If we break the ground into layers, you'll start to see why. At the surface, you usually have topsoil. This tends to hold moisture and often contains organic material and salts, which usually means lower resistivity. Below that, you'll often hit subsoil, which is more compact, holds less water, and already starts to increase resistivity. Then you may hit clay, which holds water extremely well and often gives very low resistivity values. Or you might hit sand or gravel, which drain water quickly, dry out easily, and push resistivity up dramatically. Go deeper again and you may reach chalk or rock, which can have very high resistivity, especially when dry. The important thing to understand here is that current does not travel straight down. It spreads out through the soil in all directions, following the path of least resistance. So the electrode is interacting with a large volume of ground, not just the soil directly around the rod. So two electrodes driven to the same depth can behave very differently depending on the soil that's around it. And exactly why a distribution network operator or DNO tests the resistivity of soil before deciding where to put a substation or transformer. The substation and transformer is not just there to step the voltage down, but it's there to be part of the earth fault loop path. If the ground around the substation has high resistivity, that fault return path could be compromised regardless of how well the rest of the installation is designed or installed. By carrying out resistivity testing first, the DNO can make informed decisions about where a substation is best located. Those results can also inform how the earthing system is designed, including how many earth electrodes may be required, how deep they need to be driven, and whether rods, tapes or a full earth grid are needed to achieve the required resistance. Now, although we can change the amount or type of electrodes we're installing, we can't change where in the country they need installing. Can where you live really affect your resistance readings that much? Across the UK, the soil profile changes dramatically from region to region. This is why identical earthing systems installed to the same standard can perform very differently depending purely on location. Take somewhere like Cockermouth in Cumbria. This area is dominated by clay-rich soils with high moisture retention and relatively low resistivity. Current spreads easily, which often results in lower earth resistance values without needing excessive earth electrode systems. Move east to County Durham around places like Fanny Barks and you start to see more mixed soils with clay layers interspersed with sand and stone. Resistivity becomes more variable, meaning results can change significantly, even across short distances on the same site. Drop down into lower swell in Gloucestershire and you are into limestone and chalk dominated ground. These soils drain extremely well and often dry out in the summer. The result is much higher resistivity, and earth electrodes can struggle unless depth, spacing and electrode types are carefully considered. Netherwallop in Hampshire presents a similar challenge. Chalk downlands dominate this area, and while conditions can look fine at the surface, resistivity increases rapidly with depth once moisture drops off. This is where shallow assumptions can lead to disappointing results. Head north to Penistone near Sheffield and the picture changes again. Here you are dealing with upland soils, often thinner, sitting over gritstone and shale. Moisture levels can vary hugely with weather, meaning seasonal changes can have a significant impact on earth resistance values. Clay-rich soils dominate in Shitterton in Dorset. These areas often give excellent resistivity values, sometimes lulling installers into thinking earthing is easy until conditions change or parallel paths disappear. So it's not just a one-size-fits-all approach when it comes to resistivity, which is why testers like this one from Chauvin Arnoux are such essential pieces of kit. But I've also heard that parallel paths can affect resistance and resistivity. So how does that happen, and does it really matter? The short answer is yes, it matters a lot. Because parallel paths can completely change what your test instrument is actually measuring. A parallel path is any conductive route in or on the ground that allows current to return without travelling through the soil you think that you are testing. Electricity will always take the easiest route available, and in many cases, metalwork buried in the ground offers a far lower resistance than the soil itself. On real sites, these parallel paths are common. Buried metal water pipes are one of the biggest contributors, especially older pipework that can run long distances and effectively export your test current well away from the electrode under test. Gas pipes, structural steel, cable sheaths, reinforcement in concrete, ground-mounted metal fences, and even nearby pylons can all provide unintended return paths. When your test current finds one of these routes, it will use it. The result is a resistance reading that looks very good on the tester, but that figure is no longer representative of the soil. Instead, you are measuring a combined network of soil and metalwork, which masks the true resistivity of the ground. So is there anything we can do about it? Well, you're not going to be able to rip out metal fencing or a pylon, but we can do a resistivity test. By spacing the probes correctly and separating current injection from voltage measurement, the influence of most parallel paths is reduced, allowing the test to focus on the soil rather than the installation. We mark out a 9 by 9 metre grid.
It was supposed to be 100 metres, but it turns out me and Dave can't count.
This has given us our known test area that we can work across in a controlled and repeatable way. Once the grid is set out, we can start positioning the probes. The test we are carrying out here is the 4-probe resistivity test, commonly known as the Wenner method. This method is specifically designed to measure the resistivity of the soil itself rather than the resistance of an installed electrode. The setup uses 4 probes driven into the ground in a straight line, all equally spaced. In our case, the 4 probes are set out 1 metre apart. The 2 outer probes are used to inject a known test current into the soil, while the 2 inner probes are used to measure the voltage drop created by that current as it flows through the ground. And an important consideration here is the depth in which we bury the probes, because that really does matter. As a rule of thumb, the depth of each probe should be no more than about 5% of the distance between the probes. With a 1 metre spacing, that means the probes are typically driven around 50 millimetres into the ground. This keeps the measurement focused on the soil volume between the probes rather than deeper layers of the soil which would distort the results. Once the probes are in place, we connect the leads into the tester. Selecting resistivity, we can input the parameters of our test and it will do the calculations for us. We will show you the formula in a second though. Pressing the test button and the instrument injects a controlled current through the outer probes, and the inner probes then measure the resulting voltage difference.
1 down, 90 to go.
From those 2 values, resistance can be calculated using Ohm's law, but resistivity requires one more step. Resistivity, which is represented by the Greek symbol ρ, is calculated by carrying out the following formula: 2 pi multiplied by A multiplied by R, where A is the distance the probes are apart from each other and R is the resistance that is measured between the potential probes. The unit of measurement for resistivity is ohms meter, so let's see what we get. We got a resistance of 10.4 ohms, so let's work that out into our formula. 2 pi multiplied by 1 meter multiplied by 10.4 ohms equals 65 ohm meters. By repeating the test across the grid, we can build up a picture on how resistivity varies across the site. And with the aid of some clever editing, we got this grid tested in no time at all. So what can we do with all of these readings? Well, we threw these numbers into a special Excel spreadsheet. We could then map the resistivity on the ground to see where the best location to stick a substation would be. The lighter green is the lower resistivity. Now, I've been using the Chauvin Arnoux kit for the last few weeks now, and I've been impressed with its accuracy, ruggedness, and the ease of use. They have a massive range of test equipment which you can check out using the links in the description. So there we have it. In this series of videos, we've gone from earth electrode resistance testing all the way to testing the resistivity of soil, so you know the best spot to stick a substation. And if you want to find out more about the test equipment from Chauvin Arnoux, then hit the link in the description.